Hey guys, Mr. Ray here with our next grade 10 academic lesson. Um, Not sure which lesson this is in terms of the number, but we are starting a brand new unit today on trigonometry. So good news is we're done our quadratics for the course. So I know it seems to some of you like we've probably been doing that for a couple of years, but we are now officially done. We're going to try to finish off a couple more units before we wrap the course up. So we're going to look at trigonometry. I'll talk a bit about that, and then after that's done, we're going to look at linear systems. Okay, so trigonometry, I know a lot of people, when they hear that word, they break into a cold sweat thinking this is really difficult stuff, but the word trigonometry, uh, the first part here just means uh, uh, triangles. The tri stands for three. A trigon is like a triangle, and metric or metry is the measurement of. So this is basically all we're looking at, the measurement of triangles. That's what trigonometry is. Okay, so it doesn't sound that bad when you say it that way. Okay, and in terms of measuring triangles, there's only 6 measurements that a triangle has, and that's the. I just look at the triangle here. I've got 3 angles I can measure and 3 sides I can measure. So when you talk about the trigonometry, you're just looking at determining. You're probably going to determine an angle or a side of the triangle, or maybe more than that. Okay, but that's in terms of what can we measure. It's just 6 possible things, so it's not that bad. Okay, so the first lesson we're going to look at something called similar triangles. And then all the remaining 5 lessons, 2 through 6, are looking at it from a different perspective, looking at right triangles, and then triangles that aren't right triangles, and how to measure angles based on information you may have. Okay, so this lesson is quite different than the other 5, so it's important that you get this because you will have questions during the first week's assignment on this part. So when I look at some terminology here, so the word congruent, okay, anytime you talk about 2 figures that are congruent, means they have identical shapes. So if they're identical shapes, it could have, it could be a triangle, it could be a square, and all the measurements are exactly the same between the 2 shapes. Okay, so if you looked at both shapes, you would say, oh, they're exactly the same. Okay. What we're looking at is not congruent triangles. That's pretty boring. They're just exactly the same. Similar triangles are sort of the same, but not exactly the same. Okay, so what a similar triangle is, and we'll look at the formal definition in a second. These 2 triangles are similar, but you can tell right away that they're not identical. They're not congruent. So when I say 2 triangles are similar, one thing I can conclude is that pairs of angles are the same, like based on these 2 shapes, even though this is a bigger triangle than this. If these 2 are similar, it means these 2 left corner angles are the same measurement, the right bottom corners are the same, and the top angles are the same. Okay, so that will definitely tell me that 2 triangles are similar. It's just one is a bigger version or a smaller version than the other. Okay. Now, when you look at the sides, obviously, this side is not the same as that. None of these sides are the same. But what you can say is if you found the ratio of these 2 sides, say that this side here, C, was twice as big as this side, well, that would tell you that the other 2 pairs of sides have that same ratio of size. So this side here is twice as big as this side. This side here is twice as big as that, and this side is twice as big as that. Or it could be, 1/3 the size, or 1.2 times the size. As long as that multiplier to get to the other triangle is always the same, you can say that the 2 triangles are similar. Okay, so here's the formal definition here. Here's the about congruent figures. They have the same size and shape. Um, Similar figures, which includes triangles, have the same shape but different sizes. Okay, so similar triangles have the following properties. We just talked about that. So in this case, we said that that's a symbol for angle, by the way. Angle A is equal to angle T. Angle B is equal to angle U. Angle C is equal to angle V. Okay. Now, when this is true, when we have similar triangles, I'll just add this in here. We can say, and the order I put the triangles doesn't really matter. So say I'll use it this way: triangle ABC, which is this triangle. Now, I'm not going to use the symbol equals because equals means they're congruent. Okay, so I use this little wavy equal sign. Now, when you read that really you would say is similar to. So triangle ABC is similar to triangle. Now, you'd use the letters for this triangle. Now, the letters are actually, the order are very important. It's not always going to be alphabetical order, but the way you do this is extremely important. So when I have these statements here, angle A is the same as angle T, B is the same as U, C is the same as V. That means when I create the vertices over here, the letters that go here have to match up with the order I put them over here. So A, well, that's the same as T, so T has to go first. B is the same as U, so U has to go second, and then C matches up with V. So I have to put it in this order, and I know it looks like I'm just doing it alphabetically. It turned out that way, but that's not the reason why this is true. If I switched up any of these letters or any of these letters, that would not be right. Okay, and I could have written this in any order I wanted. I could have said BAC is similar to triangle UTV because I have to switch the order of those two. Okay, so that's how you make a statement about whether two triangles are similar. So very important. Okay, now so there's if you know that this is true, that three pairs of angles match up, then you can say these two triangles are similar. Okay, now you can also look at the side lengths. You may not know anything about the angles, but maybe you've got the actual measurements of the sides, and you don't know for sure. Is this similar? Well, you do the ratio of the corresponding sides. Okay, so we'll get more into this in the examples, but you can kind of tell the corresponding sides in this case. AB, the corresponding side would be TU. So if I put that as a ratio, AB over TU, and I did the same with the other two pairs of sides, if these ratios work out to be the same value, then you can also conclude that the triangles are similar. So you could be given the angles and make a conclusion this is true, or you could look at the sides. Okay, we don't actually have the measurements here, so we can't do a calculation, but you could look at that. There's an example, first example, we're going to do this. Okay, now when you actually take the ratio and you get some number, like you might get 2 or 1/2 or 2.5, that value there, okay, I introduced it down here, but that value we call it the scale factor. Okay, so that scale factor would be what do you have to multiply to get the sides on the other. So in this case, we could say, well, maybe this ratio here is 2, like if we use the same numbers as I had before, so that these sides I'd multiply by 2 to get these sides. Well, that number 2, if k was equal to 2, you could basically say I take these side lengths and I multiply each of them by 2 to get these side lengths. Okay, so that's called the scale factor, and that's what I said down here. You're multiplying the side lengths of one triangle by k to get the lengths of the other triangle sides. Okay, now there's a strange thing here. If you took the ratios of the areas, okay, so we'll look at this in our last example. It's the least important thing of this lesson for sure. If you took the ratios of the two areas, the ratio would be the scale factor squared. Okay, so we'll look at what that means in the last example. Okay, so that value k comes up again when you're talking about comparing the areas of the two triangles. Okay, so we're going to do a couple of examples here. Actually, 3 examples. And I urge you, these questions are in the textbook. If you're not sure where, you could look it up in the table of contents under similar triangles, or you could look where the homework is and just go back a couple of pages. You'll see these. I'll probably be doing them pretty much the same as the book does, but sometimes there's differences. So we've got this picture here, and it doesn't really matter what it is, but this is a river, 2 sides of the river, and we made some measurements here. So we have 2 triangles. Hopefully you can see it. We have the little triangle ABC down here, and the big triangle CDE here. You notice the point C is common to both. It's kind of they're joined. Both triangles are joined at C. So the question is saying, are the 2 triangles in the diagram similar? And you can't just eyeball and say, yeah, they look similar. You have to prove it mathematically. Okay, so there's 2 ways you could prove it based on what we talked about. I could either compare the angles and show that I have 3 sets of 3 pairs of angles. Each pair is the same measurement. That would prove it, but you know, in this case, I don't know any angles. And you know, the idea is not to take out a protractor and measure. In this case, we've been given the side lengths. Okay, we've got all 6 side lengths. So that's enough for us to be able to prove if these 2 triangles are similar. Okay, so I'm going to start off by making an assumption. I'm going to assume that they're similar and say if they are similar, so if triangle ABC is similar to, now I have to make sure I get the order right here because I have to kind of get them in the right. So you can kind of see, you know, this triangle is not oriented the same way this is. Okay, I've got this right angle. This looks like a 90-degree angle here, and so does that. So I would say that the B and the D probably match up. And then based on the orientation, if this swivels around, the A would match up with the E, and that leaves D matches up with B. Okay, so if I'm matching the letters, okay, when I make this statement, I have to be very careful. So the A, I've already said that looks like it's about the same angle as that because of the orientation of the triangle. So that means that the E would go first, and then I look at my B. The B corresponding vertex over here would be D, and then the C and the C are the same point. So that's how I make my assumption. So if this is true, then I can look at the ratios of the sides, of the corresponding sides. So we haven't really talked about this part yet, so you need to pay attention to this part. So if I'm going to do the ratios of the sides, it's 3 ratios because there's 3 sets of sides. So I can start by that. I've got 3 ratios with 2 equal signs between them. Now up on the top side, and this is an arbitrary decision, I'm going to use all the sides from triangle ABC. Okay, you could do it differently. You could do all the sides from EDC, but I'm going to do all the sides from ABC. So, you know, you don't have to do them in any special order up here, but I could say, well, I know AB is a side, I know AC is a side, and that leaves BC as the other side. Okay, so I've got all 3 different sides from triangle ABC on the top, and then on the bottom, this is where you have to think about this. Okay, so the side AB, okay, those, think of it this way, AB are the first and second letters in this triangle, so I look at the first and second letters in this triangle, so that would be AB over ED. Then I've got AC. AC, first and third letters, match with the first and third letters here, so that's EC. And then BC, second and third letters, second and third. Okay, so I've got what should be equal. These three fractions or ratios should be the same if these two triangles are similar triangles. So now we just plug in the numbers and check. Okay, so I've got AB, that's 4 from the picture here, AB. That's over ED, which is 20. AC, that's 5 over EC, 25. Sorry, that was a 3. Oh, that's right, 5. EC is 25. And then BC is 3 over DC is 15. Now these look like they're different numbers, but all of them can be reduced. Okay, for example, the 4 over 20, I can divide both top and bottom by 4. I get 1/5. Same thing here, I can divide both of these numbers by 5. When I do that, I get 1/5. When I divide these by 3, I get 1/5. So this is a true statement, and since this is true, therefore our assumption at the beginning about these being similar is true. So therefore, triangle ABC, and you can do the one little mark there if you want, or 2. So triangle ABC is similar to triangle EDC in conclusion. Okay, so that's how you use the side lengths to see if two triangles are similar. And it's very important to make sure you define your triangles in the right order. You can't just arbitrarily choose the order of the letters. You can for the first one, but the second one has to line up with the first one. Okay. The next question, example 2. I think this is a really cool question. We're actually going to figure out how wide a river is without actually crossing the river or using a measuring tape across the river. So here's the situation here. To determine the width of a river, Naomi finds a willow tree. So let's look at what this picture is. So it's a little similar to the one above. Okay, the river is here, and we have a shoreline here where Naomi is standing, and then the opposite shoreline, nobody's over there. Okay, we want to find out how wide the river is. Okay, so there's a couple of landmarks already there. There's a willow tree here. There's a maple tree directly across. And there's a sumac tree over here. That's the only things that we have. So she actually finds a place where she has 2 landmarks that are directly across. And then using a third tree on the shoreline, Naomi plants 2 stakes, A and B. So these are just little poles or stakes she puts in. So you notice these 2, I think the first thing she would do would place a pole that's perpendicular to the sumac tree, where the sumac tree and where the river is. And then the B would be right on the shoreline in between the willow and that post she just put. So she's formed 2 triangles here. Okay. And she's done this so that they are similar triangles, and then you can use that as a method to solve. So let's just prove first that these are similar, because maybe we're just taking her word for it. Let's not do that. So in order for these to be similar, these angles would have to match up between these 2 triangles. So you can see we've already got these letters A and B. So I'm just going to use the same letters. For example, the sumac tree would be S, the maple tree would be M, and the willow tree is a W. Okay, and the A and B are already there. So I have 2 triangles, ABS and BWM. Okay, so in terms of the other important thing here is that this is a 90-degree angle, and so is that, because she positioned that post so that it was 90. And the other thing is, since these are both 90, then these two lines are perpendicular. Okay, and this is going to be important in a second. So the first thing we can say between the two triangles, angle B is equal to angle B. Now these are actually different angles, but they're the same because if you remember from grade 9, these are opposite angles. So I'm actually putting a statement here. These two angles are equal because of the fact that they're opposite angles. Angle S is equal to angle M because they are both 90 degrees. Okay, so I've got two pairs in each triangle that match up with each other. Now I could actually stop here and say, well, if these two angles are the same, then the third pair of angles has to be the same because of the 180 rule. So that's what I'm going to do. Angle A. Now notice all these angles are in the left triangle, and all these angles are on the right. That's important. So the third angles in each triangle have to be equal because the angles in a triangle add up to 180. Now you could also say that these are equal because of, do you remember doing the angles with parallel lines? So this would be like the Z pattern. So angle A and angle W are the same because of the Z pattern, and so that's a very valid reason for saying that these two are equal. But you could also say, since we already have two angles in each triangle, the third one has to be. Okay, so therefore, here's our important statement that allows us to do the rest of it. So I'm going to name this triangle, and I'll put this in alphabetical order. Triangle ABS is similar to, and now here's where I can't be arbitrary. I have to match these up so they match. So angle A and W are the same. So that means W has to be the first angle there. B matches up with B, so that means I have to have a B there. And S matches up with M. So that is my similar triangle statement. Okay, now here's where we kind of did what we did in example 1. I'm going to put out the ratios of the sides. So since these are similar triangles, therefore I'm going to put my 3 ratios, and I'm going to put the sides of the 3 sides. So I've got AB, I've got AS, and I have BS. These are the 3 sides from the first triangle. Now I have to match these up to the corresponding sides. So the corresponding side of AB, first and second is WB. Corresponding side of AS, 1 and 3, 1 and 3, WM. And the third one, BS, second and third, BM. Okay, now I can go back and start pulling out some information. So I didn't really talk about these measurements, but these measurements, you can see they're all on the shoreline where Naomi is. She's measured the distance from the sumac tree to that post, sumac tree to that post, and then from the post to the maple tree. So those are the only measurements, and you can see she didn't have to get wet to do that or cross the river. She just got those 3 measurements, and that's going to be enough. That's going to allow us to figure out how wide the river is. Okay, so if I'm looking at this diagram, well, where's the width of the river? Well, that's this over here. This side is actually the width of the river. That's what we're trying to get. Okay. All right, so what I'm going to do now is start filling in the information. So some of the stuff I have, some of it I don't have. Let's just see. Okay, so AB we didn't measure. Now she could have measured that, but you're going to see it's not important. So AB is just AB. We don't know what it is. WB, that part, don't know that one either. So that was kind of useless. AS, well, AS we do know. That's 8.4. WM, well, that happens to be the width of the river. So let's just call that X to indicate that's what we're trying to get. Sorry about that. There you go. Okay, and then the third ratio, BS, we do have, and that's 9.3, and BM is 24. Okay, so we have these three ratios, and this is sort of like an equation, but it's like it's got a left side, a middle, and a right side. So when we're solving this, we only use two of the three ratios, which is good because this ratio here was completely useless. Okay, so we can't really use that. Now the rest of it, we've got 3 out of the remaining 4 values. So we're actually going to be able to solve for x. Okay, so I'm going to take these two ratios, that little mini equation, 8.4 over x is equal to 9.3 over 24. Okay. Now there's two ways you can do this. A lot of you would say, well, let's just cross multiply. 8.4 times 24 is equal to x times 9.3. That's okay. Another way you can do this, now you can't just multiply everything by 8.4 because the x is on the bottom, and that's a bit of a problem. So one thing you can do, if you have a fraction equals a fraction, which we do have, well, if we flipped each fraction upside down, that's going to be equal to, because the original fractions were the same. So I can change the equation so that it looks like this. So I flip these and I flip these. 24 over 9.3. And now you can see, well, if I want to get x by itself, I just multiply both sides by 8.4. So I'm going to get this, 24 times 8.4 divided by 9.3. And when I calculate that, that's equal to 21.7. And the units are meters from the picture. So that allows us to conclude that the width of the river is 21.7 meters. Okay, and that's pretty cool that you could actually figure out the length of something without actually being able to get to the other end. And that's a thing with trigonometry, is it's used all over the place. Like your GPS in your phones and in your cars, that uses trigonometry to find your position on the earth. Also, if you want, astronomers, when they want to know how far away a star is, they use things like trigonometry. They've got newer techniques now, but originally when that field was starting up, trigonometry was a huge part of what they did. Okay, so it's an interesting field that allows you to get information that you think that you might not be able to get. Okay, and we're going to be doing more word problems later on with other examples. Okay, so we have one more example, and this is the one that had to do with the area. If you remember, go back to that page. So we just kind of skimmed over this, but if you can find out that scale factor k, and you know one of the areas of the two similar triangles, you can figure out the area of the other triangle. Okay, so that's what this question is based on. Okay, so we have this is kind of looking from above. We've got a city map here. We got Main Street, we've got Queen Street, we've got a railway, we've got King Street. So this industrial zone that's bordered by these two streets and the railway track, and then we've got this smaller area here that's bordered by Queen Street, the railway, and Main Street. They want us to figure out the area of this industrial zone. Okay, so some of the things, the measurements we know is it's 1 kilometer from there to there. It's 1.4 kilometers from the perpendicular there to where that point is, and the length of King Street on this side is 3 kilometers. So the first thing we're going to do is prove that these two triangles are similar. and then use tools from that. So first thing we got to do is label these points. We have to have that. So I'm just going to kind of go around A, B, C, D, E. Okay, and now we're going to prove that they're similar. The one thing that's not on this picture that was mentioned here, let's just read it again. Shaded areas to be industrial zone. Find the area of the industrial zone. Assume that King Street and Queen Street are parallel. So you could kind of add these little parallel symbols here if you'd like. But that's important for this first step. So angle, well, the obvious thing is angle C is equal to angle C because they're equal. Well, because they're opposite, they're equal. Opposite. So whenever you're doing this, you can make your statement. These two angles are equal, and then put a one-word reason inside here. So these two angles are equal because they're opposite angles. And then because these lines are parallel, that brings out the Z pattern, okay? So remember the Z pattern, this would be the Z here. So that tells us angle B is equal to angle D because of the Z pattern. And also A and E are the same, are equal because of the Z pattern. Now, if they didn't tell us that those two streets were parallel, we couldn't even do this. Okay, so that was extremely important to know that. Okay, now since we've got these three pairs of angles are equal, we can now conclude that these two triangles are similar, but we have to put it in the right order. So for this triangle here, I'll put this in alphabetical order, ABC. Triangle ABC is similar to, and now we have to be careful, we have to match up the letters. So A goes with E, B goes with D, C goes with C. So in this case, they're not alphabetical, but it is correct because they match up based on the angles that match up together. Okay? Now that we know these are similar, I'm actually going to figure out the scale factor K. Like, what did we have to multiply these sides to get these sides, or vice versa? Okay, and I happen to know two sides. I know AB and I know ED, so I'm going to use, so AB and ED are corresponding sides. So AB over ED, that's going to be 3.0 kilometers over 1.0. So that's K equals 3. So that basically means if I want to know the side lengths of these sides, I need to multiply the corresponding sides here by 3 because I already knew one that worked. Okay? Now, the ultimate goal is to get this area. So now that I've got the scale factor K, I want to figure out the area of triangle ABC. Sorry, CDE. So the area of triangle CDE. Now, it just so happens they gave us everything we need to know. Okay, so if I'm looking at this triangle, I've got that side and I've got that. Now, if you turn this on its side, you'll see that, oh, I know the base is 1 and the height is 1.4, and that's what you actually use to get the area of a triangle. So it's the base times height divided by 2, and the base, we'll call that 1.0. The height was 1.4 divided by 2. So if we do that math, we get 0.7, and the units are kilometers squared. Okay, so the area of that triangle, or that zone, is 0.7 kilometers squared. So if I want to get the area of the industrial zone, that's area of triangle ABC. So remember go back to the formula. It's not written in the way I want to use it, but basically I got to multiply the smaller area by K squared. So that's going to be the area of this triangle, triangle CDE, times k squared. Okay. Now, we know both of these. We know the area of triangle CDE is 0.7. I'm not going to put the units in here, but we'll remember. And the k squared, well, the k was 3, so that's 3 squared, which is 9, and 9 times 0.7, 6.3, and the units are kilometers squared. So therefore, the area of the industrial zone is 6.3 kilometers squared. Okay, and we answer this question by using similar triangles. First of all, we had to prove they're similar triangles before we could use any of those special tools. So once we proved by looking at the angles that they must be similar, then we looked at the ratio of two corresponding sides and got the scale factor of 3, meaning that these sides are 3 times bigger than these sides. And then we calculated the area of the small triangle, base times height divided by 2, and then we used the fact that if we multiply the smaller area by k squared, we get the bigger area, and it was 6.3 kilometers squared. Okay, so I know that was probably a lot in one lesson, but hopefully that makes sense to you. If not, just go look at the textbook. Maybe their approach is slightly different than mine, but I think it's pretty close. You can also look on YouTube for videos on similar triangles if you'd like. And then what I'd like you to do is try some of these questions. Make sure you know what to do. There'll probably be a couple of questions on this week's assignment based on this lesson. So it is important to understand what you're doing here. Okay, so hopefully that makes sense. And on the next lesson, we're going to get into right triangles. And you're going to learn how to finally learn how to use some of those strange buttons on your calculator that you never knew what they were for. Okay, so have a good day, and we'll talk to you in a couple of days.